Let's recap again. Chapter 15, continuous random variable. What is continuous again? Can I please have Sebi? What is continuous? Something that you can't be counted, so uncountable. So a variable that you cannot count. Give me an example. Give me one example, Jack. Time is an example of a continuous variable. What else, David? Height. Height is another example. Anything that when you measure has decimal points, infinite decimal points, they change. Whereas shoe sizes, 12, 12 and a half, 13, 13 and a half, 14. That doesn't change. You don't ever go into a store and say, I'm about 13.76. Okay? You go in and say 13 and a half or 13. So, uncountable would be time, height, weight, temperature. All of those are uncountable. Okay? Once we've got that, the problem with uncountable variable is that you can't find the probability. And the example I classically gave you was that if you had a string and you randomly cut it, it's impossible to find for one specific cut what's the chance of that occurring. It's like me saying choosing someone in this class, what's the chance of me choosing someone at a weight of 73.122 kilograms? I don't even know how to figure that out. Unless I say, what's the chances of choosing someone between 70 and 80 kilograms? Now I'm starting to get data. That's possible to do. Yeah? And because it's a region, that leads on to one theory. So what was that one concept? What do you need, Luke? Yep.
Probability density.
Good. Probability. And you'll know in the exam, they'll tell you it's a probability density function because they have to. They can't assume anything. They tell you it is, and then you can assume. So if it's a probability density function, what does that mean? What does that mean, Rex? The area is equal to 1, good, because probability density function, now you're going to use this. It has to be this so that you can use this to model a probability situation. That's the only time then you can calculate the probability of these variables. So the only way is, yes, the area has to equal to 1. Why? Why does the area under a particular curve have to equal to 1? Why? Someone explain it to me. Percy. Why does it have to equal to 1? Why can't it be 10? Why can't it be 2? That's a good question.
That's all probability added together.
Yeah, and remember probability by definition we understood it's either 0%, you either don't know it, or you do know it, it's 100%. You can't be 110%, that's why it's between 0 and 1, because 100% is 100 out of 100, which is 1, yeah? So it makes sense that if you summed all the probabilities together, it has to equal to 1. It's like saying when you roll a dice, 1, 2, 3, 4, 5, and 6, chances of rolling a 1, you'd say 1 out of 6, 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 1 out of 6. And if I told you to sum all those chances together, well, naturally, you got all possibilities. When you roll a dice, what's the chance of you getting 1, 2, 3, 4, 5, 6? 100%. I'm sure that I'm going to get one of them. Yeah? So that's why it makes sense that if you sum all the probabilities, they have to equal to 1. What's the other condition? What's the other condition for a probability density function? Can I please have Gary? What do you need?
Function constant with or equal to 1. I is equal to 0.
Good. Now the question is why? So it's not about memorizing. Why does the function have to be greater than or equal to 0? Can I please have Stephen? Now. Why not? So what has that got to do with the curve function? It must be positive. Okay. Now, what he was just saying, just breaking up what he's trying to say. A curve, f of x is a function. Function could be anything. So I'm just going to draw a curve. That's a function, right? Remember, we said the area under the curve is the probability. So if area is under the curve, then we just said probability has to be, as he said, greater than 0. It has to be positive. So it doesn't make sense if you have a curve under the x-axis, because then the area is negative. But if the area is negative, that implies that you have negative probability. But that's impossible to have. How do you have negative probability? It doesn't make sense. You only have 0 to 1. So that is why the curve, or the function, it can't be below the x-axis. Because as soon as it's below the x-axis, the area is negative. If the area is negative, you've got negative probability, which doesn't make sense. Okay, so therefore, it can't model a probability situation. So those are the two conditions that are required. It needs to, 1, curve needs to be above the x-axis. 2, the area under the curve, which is the probability, has to equal to 1. Because you sum it all together, it has to equal to 1. That's the logic. Now, once you have these two conditions met, then you call it, whatever that curve is, it could be any curve, whatever that curve I just drew, if it happens to be that the area does actually equal to 1, and it's above the x-axis, now I can say that is a PDF graph. Okay, it's a probability density function. That's what it means. So as soon as you have that, now you can analyze it. You can analyze for 50%. You can analyze for 20%. You can find the chances of when will it be 80%. Or x is greater than 2, whatever it is, whatever this x-axis represents, whether it's height, time, weight, whatever it represents, this x-axis, this x variable, whatever it represents, you can now find the probability. It's possible. So it's like saying, if I said you're a weight of 70 kilos to 80 kilos, it's this region. I'm working out the area, which is the chances, the probability of 70, x is between 70 to 80. That's what you're actually saying. Does that make sense now? Yeah, so when you're actually finding the area, if I said, I want to find out the number of people, the chances of you guys here, this is the curve, the chances of you guys weighing between 70 to 80, that's my area, that's my strip. That would be talking about the probability of getting that. And you're just finding the area between 70 and 80. So that's just saying integration of 70 to 80 of your curve dx. That will be the probability of choosing someone between 70 and 80 kilos. Okay, because kilograms, which is my x-axis, that is my continuous variable. Does that gel in now? Okay, so that's what chapter 15 is about. And you're going to use chapter 15 to do chapter 16. Yeah? But that's the concept. That's the first thing you need. It needs to be a probability density function. Okay, and that's different to discrete. Yeah? All right, so now we've got probability density function. Now let's go to chapter 13 stuff, which links to chapter 15. What was my E of x? What does E of x mean again? What's E of x mean, Jack? It is your expected value, but let's speak in English, Amir. What is expected value? Good. Sum of all numbers divided by number of numbers, that which is true, number of numbers. Alternatively, this is the same thing as saying the average, okay, or the mean. So the expected value is what I predict, what I expect you to get. It is the average, okay? What's the theory again? There was a formula we learnt in chapter 13 that summarizes E of x. Because we know sum of numbers divided by number of numbers, that's what we learnt in 7 and 8. And then we were able to summarize this when it came to probability. What was the formula again when it comes to probability for E of x in chapter 13? What was that again, Frankie? E of x. No, NP is your binomial. NP, which is correct. E of x, this is the common mistake. I'm just asking for the theory first. This is for binomial. It's only when, see, binomial only happens, you can only use NP if you only have two outcomes. So you either have it or you don't. Then it makes sense. N times P, that came from this theory. Now I need to know what this theory is, because whatever that theory is helps you remember chapter 15, E of x. Okay? So what was the theory again? What was the theory again? Let's pick someone else. Who am I picking? Stephen. Zhao. What's E of x equal to? Chapter 13. Discrete variables.
What was it called? The sum?
Yeah, the sum. Good. We're on the right track.
Times the probability.
Something times the probability. Yes, you're right. What is that something?
X.
X. Fantastic. X, which is your variable. See, in this case, this is just the theory. See, x can be discrete. X can be continuous. We don't know what x is, but we know if you take your data times your probability, it was the same thing as doing the sum of all numbers divided by number of numbers. And I showed you the proof for that. Yeah? So, using this theory now, That's for the expected value. I want you to tell me for chapter 15, what was the formula to find the expected value? If you know it's x times probability of x. What was it again? Can I please have Alice? Good. It's x times the area under the graph. So if you think about it, area under the graph, didn't we say up here before, area under the graph was integration from negative infinity to infinity of f of x. That's the probability. So the area under the graph is integration negative infinity to infinity of f of x dx. The way they wrote it in your textbook was integration negative infinity to infinity of x times f of x dx. It's the same thing. See the sum, the sum here means add all the probabilities times x, right? But this is summing. See, this is summing all the areas from negative infinity all the way to infinity. You're summing all the areas, which is all the probabilities. It's the same thing. Both of these are the same theory. So if you understand chapter 13, it's the same thing. You're saying x times the probability, and we know probability is the area under the curve. So the area under the curve is the probability. So you just replace it. You're like, oh yeah, well, P of x is that. That's your probability times your x. So x times your probability, sum them all together, this should be the average, because that's what the theory was. Does that make sense? Yes? Okay, now, once you got that and you understand that drift, then you can now do same thing with the variance for chapter 13. So this is chapter 14. Chapter 13, again, going back to chapter 13, variance. What's the theory for variance again? I always use that graph where I expect what you get, you minus your data, whatever it was. What was the formula again? What was it again? Amy? I keep doing this until you all know it, and when I ask you, you're going to answer. You can answer immediately. That's what I want. What was it again? E bracket x mu squared close brackets. Okay, now again, think about the theory. What is the variance? Variance measures on average, it measures how bad is my prediction, the error of my prediction. So it makes sense. How do you find out the error of my prediction? Take what the actual data is minus what I predicted you got. See, minus that tells the difference, how bad my error is. But sometimes I have a negative, sometimes I have a positive. That's bad, because I can get a 0. There's a net 0 there. So I don't want that negative. I square it. See, squaring it removes all that negative possibility. Then I find the average. See, E of this means find the average. So overall, how bad in the long run, how bad is my prediction? That's what the variance is describing. Okay? And see, now using this theory, it's the same thing for chapter 15. If you know how to do E of x, see, this is E of x. For chapter 13, E of x is this. It's x times the probability. So then E of x is x times the probability. So then over here, if variance is E of this whole thing, x minus mu all squared, then for chapter 15, which I'll do here, chapter 15, the variance has to equal to what? What's the variance equal to? Using the same sort of logic. I'll just zoom it out so you can compare the two. See, I'm going to highlight what I want you to compare with, and then you can figure it out on your own. This is E of x, chapter 15, and this is what you know. So then this is chapter 13. I want to find the same thing for the variance. What is it equal to? Yes, Amir, what is it? Integral of negative infinity to infinity, yes? X minus mu squared times f of x dx. Fantastic. See, this is the same thing. This here, you said E of x. See, that's an x variable. You had x times p of x. So if it's x, then it was x. Then if it's x minus mu squared, then it becomes x minus mu squared. That's the same thing. You're just transferring it. See, if you knew over here, if I just zoomed in here, if this is our definition, then the variance by definition, we said it was E of x minus mu squared. So what's the difference between the two? It's just, instead of x, that was x there. So instead of putting the x there, I'm now putting x minus mu squared. So this now becomes x minus mu squared times negative infinity to infinity of f of x dx, which then if you can times it by this value, then you can bring it back in, and that is exactly the same as what Amir just said. That's your variance. See what I'm trying to do? Chapter 13 links to chapter 15, but it also links to chapter 16 and 17. It's all the same thing. Everything you do goes back to those two theories. Yeah? And those are your two formulas for one for variance, expected value, but I wanted you to understand what it means. So expected was what you, on the long term, in the long term, what is the average, what is the mean? Variance is the expected, it's the expected, or the on average, how bad is my error? But what's the issue with variance? Because I'm still missing one more thing. What's the issue with variance? So with this theory, what is wrong with this theory? What's wrong with the concept? So I said, take your data, minus what I expect, I squared it, and find the average. Sounds right. What's wrong? There's something wrong about it. What's wrong? What is wrong? Anyone have a clue? The hint is, why then do you need standard deviation? Why do you need standard deviation? See, standard deviation says this. Standard deviation of x is equal to root, or whatever your variance is. Why do you have to do that? That's from chapter 13. Why is this the case? What was it again? Someone explain it to me. I'm going to randomly choose. Let's go with Josh and you in. Why? Why do we square root? Perfect. It literally is, remember this data here, if you think about it logically, if I drew my graph, this is my prediction, E of x, and let's say this is your data. Let's say you got 80 and I predicted you to get 70. But then let's say someone else in this class also had a prediction. I predicted that they would get 80, but they got 90. Okay, so I predicted they would get 90, but they got 80. Okay? Now you got two datas. One is I'm 10 off, positively 10 off, and the other one is I'm negative 10 off. Okay? Both of them I'm equally as bad. But if I sum them together, 10, that's my 10 error. I've got a 10 error here, and if I sum them together, that's a problem. That tells me 0. So that tells me I have 0 error. I've made no errors at all. But actually I did. I had 10 error here, 10 error there. On average, it should have been 10 plus 10 divided by 2. So on average, I made an error of 10. True? 10 plus 10 divided by 2, that's my average. Sum of all numbers divided by number of numbers, that gives me 10. So it makes sense. I'm on average, I made 10 error. But how do you remove that negative? See, that negative is an issue, because if you have negative 10 plus 10, it gives you 0. I'm not 100% accurate. I'm actually 10 inaccurate. So the only way to resolve that issue was, you said, square it. Square all the data. So if you square this, now it becomes 100. This becomes 100. This makes sense. See, now both of them are equally as bad. Equally as bad. So if you found the average of this, 100 plus 100 divided by 2 is now equal to 100, which is true. It's true in the sense that those two are equally as bad. But what's the problem? I'm not 100 off. I was only 10 off. I was only 10 off. So the variance is nice because you can compare that. You can compare all the errors that you've made that are the same. But the problem is you exaggerated how bad I was. So that's why the standard deviation, if you square root it, if that's my variance, if I square rooted 100, now it makes sense. I'm actually 10 off. That's my error. That's on average, I am 10 off. It makes sense. That's how I want you to understand what a standard deviation is and what variance is. Okay? Try to think of this example. Every time you're trying to understand the concept, try to think of this example. Plus 10, minus 10. If you found the net, if you found the average, it would have been 0. That's a problem. Square it. Square it is your variance. But if you square it, it's exaggerated. So how do you unexaggerate it? Square root it. Because you squared it, then square root it. You're back to positive 10. Because every time you square root, it becomes a positive value. That's why you have a standard deviation. Does that make more sense now? Yeah? Okay, good. So that just means for chapter 15, standard deviation is the same thing. Whatever you do here, whatever the answer is for that, you can now put it into standard deviation of x is equal to the square root of variance. But doing this for chapter 15 is hard. Why? X minus mu all squared times f of x. Too confusing. Too hard to do. There had to be a better way to do it. So, there was another, what we call computational formula. One that you can type. It's easier to type. What was the formula for this one again? So it's still variance. This is the theory, which is correct. What's another way of doing it? What's the formula for variance? It's from chapter 13. What's the formula for variance? Computational formula. Anyone remember? Do you have it, Stephen? What was it again? E of x squared, good? Good. Okay, this is your computational formula, which actually, if you look at the proof, which you don't need to know, the proof for this formula comes from here. And they figured this one out as a computational, meaning it's easier to solve with your calculator and whatnot. Okay, now this one you can do for chapter 15. How? So remember, you said before, if it's e of x, this is x. If it's x minus mu squared, this is x minus mu squared. So if you want to find e of x squared, it's the same thing. This will now be x squared times the probability, which actually ends up being the same thing as saying negative infinity to infinity of x squared times f of x dx. That's what e of x squared is. Okay, so that means you can come back to this and say, oh, I know what that is now. That is integration negative infinity to infinity x squared times f of x dx minus, and you know it's the square of e of x. E of x was integration negative infinity to infinity of x times the probability all squared. Now that's possible to do. So that's why now you can find out the variance for chapter 15 using the same theory. See, each and every one, I don't want you to memorize all this. See, they all make sense. You can find them out. Okay? But there you go. That's chapter 15. What I want you to do in this first half of the session is to work on that theory. Every part of this exercise, there's only 3 exercises, 15A, 15B, 15C. I've covered them all. Okay, so I've covered, this is 15B, expected value, 15C, variance and standard deviation, yeah? And 15A, PDF. Okay, so if you think about it, PDF, 15A. 15B, expected value and the median. 15C, variance and standard deviation. Okay? All right. Oh, actually, no. Wait, there's one more thing. I've forgotten about this. Just terminologies, things that you learned back in year 7. Let's jump down a bit. Back to year 7. Anyone remember what IQR stands for again? Interquartile range. But what does the interquartile range mean? See, the range means the largest value to the smallest value. But then what about interquartile range? What does that mean? Anyone remember? Good. It's the 75% to the 25%. So what you're trying to find is what is the range, which is how far is it from 25% to 75%. Okay? Now, in terms of chapter 15, how do you figure that out? You think about it logically. Let's say the curve looks like this. The area under the curve will equal to 1. Equal to 1. So this area equals to 1. All you're asking when they ask you to find the interquartile range, they're just saying find the 25%. So when is it 25%? And then when is it 75%? Find that area. Okay, that's all they're trying to say. So how do you find 25% and 75%? That is really just trying to find the area when this is 25 and find the area when this whole thing is 75. So how do you do that? Area under the curve is just between, let's say, negative infinity to infinity of f of x dx. The area you want it to be 25%. So 0.25. Work out for the value of m. Next one, if you want to find when will you have, because when is this value? This is x and this is x. We want to know when it'll be 75%. So same thing, 75% is 0.75. f of x is the curve. So area under the curve, when is the area under the curve? Which means from negative infinity up until a certain value, that value will give you 75%. Okay? If you don't know what I'm talking about, let's think of it this way. If this is my curve, I'll do it like this. Easy, yeah? Let's say this was 10, and the area here is half. The height here is half. If I asked you when will it be 100%, 100% means 1, area of 1, right? Right now, actually that's not even 1. Let's do 1 here, sorry. Wait, that's not even 1, that's 2. There we go. Okay, now the area is 1. Area of this rectangle, true? The area of this rectangle is 1. It's a probability density function, true? Area is 1. I'm asking when, so the word when, will I have 100%? You would say when x is 2. If I ask you when will I have 50%? 50% means I want this area to only be half. So 50%, if that was to be 50%, you would say it's 1, because you did half, or x when x equals 1. Yeah? And if I said, when is it 25%? Well, you're really just looking for this. You're just looking for, from here to here, that's when you have 0.25. That's when it's 25%. And you're asking when. So when talks about this. So how do you write that? How do you write that? That's just saying it's from your graph, whatever your graph is, f of x. Your lower endpoint, in my case it's 0, up until this point, x value, this is x, and I want the area to be 0.25, or the probability to be 0.25. That's all I'm doing. Okay, so if you found the 75% area minus the 25% area, you get the interquartile range. Okay, and that's what this is. Whoops, where is it? That's what that's trying to say. Okay, so in a nutshell, I guess I'm just trying to say find the 75% area minus the 25% area. That is your interquartile range. Okay? Any questions there? Because I'm going to recap this again. I'm going to keep recapping until you know chapter 13, 14, 15 almost off by heart. Okay, because I'm just talking about theory. Talking about where it comes from. And you can play around with the calculator and whatnot. Yeah? Alright. On that, I want to stop the video now, and then you can watch this again and hear me harp on about the same thing over and over. Alright, here we go. Otherwise, start on chapter 15.